So we have our Norton's equivalent and Thevenin's equivalent. Okay. So the Norton's equivalent circuit looked like this. So we have our I Norton. Yeah, previously I wrote ITH, but should be, doesn't matter what I'm denoting it. Okay, so let's say this is R. Usually we denote this as RO. RO means output resistance, and we'll talk about that more later. We talked about this briefly last class, right? So let me refresh. So if you have a current source, what is the output resistance of an ideal current source? Okay, all right, let's see. Ideal current source output resistance. Option A, 0. Option B, infinity. Right? How many say option A? How many say option B? Okay. So when we have multiple choice questions in this class, you have to pick one. Okay. All right. So I'll give you a few minutes to think about it. You can discuss it with each other if you want, and then we'll do the poll again. Think about try to refresh what we thought about in the previous class. If you don't remember, think about what it should be. Right? Right. Think about what the definition of a current source is. Right? Current source means no matter what you connect, right? You should be drawing the same current. Voltage source means no matter what you connect, the potential difference between the two terminals will be the same. Right? So if that is your ideal sources, then for an ideal current source, what should be the output impedance? Okay, so I'll give you a minute, maybe team up with somebody, discuss, and then I'll take a poll. Ronaldo, maybe team up with Lindsay. Ronaldo, right? Is that correct?
Yeah.
Okay.
For a current source, you want all the current to go through that outside, so you don't want anything going through the resistor, so it makes it too high. I want to go that way, so that way go to the outside. For voltage, you don't want to have zero. You don't want to have a drop across that resistor. Zero means zero. Voltage means zero drop across.
Okay. All right. Any answers? Let's do the poll now. So now that you got a chance to discuss amongst each other, let's do a poll. How many say A? Okay, there are 2 options for A. How many say B? Okay, and there are 5 options for B. Okay. So now here's what we're going to do. People who said A are going to explain to people who said B why A is correct. Okay.
So going across the shorted circuit, you would want the resistance and the current output to be not the current, the resistance to be 0, so it doesn't.
Okay. So let me try to figure out what you're saying here. So what you're saying is, if I short it, okay, if I short it, all right, then what?
Then basically the current will be flowing through the circuit completely without it having any resistance.
Right, so current will be going through here, right? So this will be I now. Okay.
And basically we want no resistance for your current, so it would just be flowing through.
Right, so now, but the output resistance is RO, right? We're asking about what is the ideal value of RO, right? So now from this, how do you go, from this step, how do you go to the point that RO should be 0? Right, you see what's going on here?
Yeah.
So from here, you know, the point is, how do we go from this, saying this, to RO should be 0, right? That is not clear to me at this point,
Yeah.
right? Okay, any other?
It might be clear if you like make that R0 just an actual line, like natural zero.
Okay.
Natural line, so then maybe that would be.
Okay, so let's do that. Let's say if instead of having this, let's say if we had this is I open, and then if we had this as our arrow, right? And then if we have this, now how much current will be going through here? Like as you said, if we assume that this is 0, it's an ideal for current source if this is 0, and if this is 0, right? How much current will be in this part of the circuit?
All the current will be flowing through that.
Why?
Because
So let's talk about it from a limits perspective. Instead of having it because if both are 0, then it's very difficult to realize. Right? It's mathematically a tricky situation there. Let's say both are very small numbers but positive. Then how much current will be going through here? Let's say it's 0.00001 ohms. Both of them are 0.0001 ohms. Then how much current will be going through each part? Both of them are same.
we'll split on
They'll split evenly, right? So there'll be ion over 2 here, and then ion over 2 here, right? So as the limit of those resistances tends to 0, then we would assume that this pattern remains the same, right? So the output resistance is actually 0. When you short your circuit, only half a current will come out. So that's not acting like a real ideal current source, right? So what should be the right answer be? So people who actually came up with infinity, what was your reasoning?
So the current flows with the least resistance. And since there's no resistance coming out of the box, and you have a high resistance
Inside the box?
inside the box, that resistor, that little part of the circuit becomes an open circuit. And since it's an open circuit, no current will flow through there, so therefore you will have.
Right? So if RO is infinite, that means it's not there. Then you get the entire current through your short circuit, right? Or whatever you connect over there, you will get the entire current through that. If this is not there, right? It's not there means infinite resistance, right? So think of it. It's like ideal current source. You want to draw as much current as possible, right? That means there should not be current loss inside it. If you don't want any current loss inside it, then it should be open. Okay. So the correct answer would be B. Okay. Right. So similarly, let's talk about Thevenin's. This is the same arrow. This is the same arrow because you're measuring the resistance across the 2 points of the same box. The resistance won't change, right? All you're doing is switching off the power supplies. So that the equivalent resistance should be exactly the same because it's the same box. So RO will be also the same. Okay. So now this is the Thevenin's equivalent. Okay, let me just put a box here so that we'll know where the box is. Okay. So now in here we are showing a voltage source. Ideally, for a voltage source, what should RO be? 0, right? It's obviously opposite of current source. So the last class there was a question about when would we use one of these? When would we use this over that, right? Because it's the same RO, you just depends on the value of RO. But the value of RO is very high relative to what you want to connect to it, right? High also is always relative. So if it's high relative to what you want to connect to it, you model it as Norton's. Right? So that you can approximately say all the current will come through whatever you're connecting to it. If RO is very small relative to what you're connecting to it, then you use the Thevenin's. Okay. All right. Now we said it's the same box, right? So it's the same box. That means whatever you connect to it, let's say I've connected a resistance here of 1K, and I measure the current through it. I should measure the same current if I connect the 1K here, right? Because it's supposed to be the same box. So that means there has to be a relationship between this current and this voltage. Okay, so now this is a task for you as a class, again, in groups. What is that relationship? Again, take 2 minutes, work in groups, come up with that relationship. Answers? I want the relationship between I and O as a function of VTH. What is that F?
Just I naught times RO.
Okay, so have one option. You're saying VTH is I and O times RO. Okay, let's see any other answers. Any other answers? Okay, so how many got A? Everybody. Okay, so then I would need a volunteer to come and solve it on the board. Who? Noah? Noah, right?
Yes, sir.
Okay, so we have a volunteer. Okay, so Noah, your job is to convince everybody that what you're deriving is correct. Okay?
That should be easy. It's right because it's right.
And
Probably wrong.
if you agree his solution is correct, then I would assume that, and if you don't make any oppositions, that I assume you agree with him. Okay?
So I guess we'll start with Norton first.
By the way, when we finally have the cameras of Panopto working, we will be able to record all this stuff. At this point, we cannot.
Alright, so we're trying to switch it to voltage Thevenin. So you take your current source and you multiply it by your resistor. V Thevenin. And then what you do is, to be equivalent, is you take the resistor and you put it in series with your voltage source, your new V Thevenin. Now, you have it like this. And always, no, whichever way the direction of the arrow is going, minus the
But
bottom,
so-
plus the top.
We wanted to derive that equation, right? So you just gave it.
Here we go.
Think about it. So start with the assumption that, they are the same box, right? Both of them are the same box. That means they should behave the same way. So if they have to behave the same way, we already know that these two are same, right? So if these two should behave the same way, that means there has to be a certain relationship between these two, right? They cannot be independent. So start with that. They have to behave the same way, and then derive it. So if they have to behave the same way, let's say, if I give you a circuit, I'm asking you, see its behavior. What would you try to see? What would you try to measure? to see a circuit behavior. You have like voltages and currents, right? Okay.
I guess I would just measure with the voltmeter across these two
Okay.
to get my voltage.
All right. So then, if you measure the voltage between these 2 points, it should be the same voltage if you measure between these 2 points, right? But now you know what the circuits are, so you don't need a multimeter. You can calculate the voltages, right? So what would in this circuit? What is the voltage drop between this and R?
It's I not R.
Okay. In this circuit, what is the voltage drop between this?
It's voltage drop between those two.
Between this point and this point.
It's R. Whatever your current is times R.
If you, so what? Okay, how much current is going through R?
V7 divided by R now.
In this circuit.
Yes.
There's no current going through it.
Right.
Oh, wait, it's open circuit.
Right. Exactly. Right. So there is no current going through R. How much drop is across R?
0.
What is the voltage drop between these 2 points?
Yeah,
What is the voltage drop between these two? What is the voltage drop between these 2 points?
V7.
Right, but in terms of
case, I not.
times R. And they are the same box, that means they have to be equal. Yeah.
Alright, yay. Alright, anything else for that?
Right? So there you go. That's it. It's that simple. That's how you convert one to another. Right? You're saying they're modeling the same box, they should behave the same way. That means if you measure the voltage here, it should be exactly the same as the voltage you measured here. You get that. Right? Okay. So first of all, Noah did pretty good. Sitting there is very difficult, very different than standing here. Right? And then, standing here and thinking very clearly is not that straightforward. So, but he did very good.
I'm only going to myself. I'm going to do that every night.
Okay, so now you know why we do that conversion, right? So another lesson we learned here is never try to remember formulas. If you don't know where the formulas came from, remembering them is almost useless. Okay, so the same thing goes for me. If I just tell you, hey, this is what it is, take it for granted, you should say, hey, no, I'm not going to take it for granted. Tell me why that is so. Right? You should hold me, to explain everything why I'm saying why this is so. If I don't say that, you should ask me, hey, why are you saying that? I don't see it. Okay. So, and the reason is, if you remember formulas now, 2 years from now, you will forget it. If you know where the formula came from, 2 years from now, you'll forget the formula, but you can derive it. Right? That's the spirit. Okay. So now we know what F is, and A is the correct option. Okay. All right. So now so far, in fact, we've said we can make these sort of equivalent circuits even when we have capacitors and inductors. And we also made a more general statement which says we can do that whenever we have a linear circuit. Okay. So that means we should know what a linear circuit means. Right? In general, we should know what a linear system is. Okay. So one thing about engineering is pretty much everything is a linear system. If it's not a linear system, you will try to find a way to make it a linear system and analyze it. Okay? And there are many reasons for that, because linear systems are extremely easy to analyze. And that's so if you have a very complex nonlinear system, and we're gonna see nonlinear systems in this class, we're gonna say, okay, hey, if you restrict your input to this range and output to this range, it's approximately linear, we'll assume it's linear. And then we'll just restrict those voltages like that. That's what we're gonna do. Okay, so we'll try to find a way to make our systems linear and then work there. Okay, if it is not possible to do that, then we'll have to work with nonlinear systems. But if it is possible, do as much as you can to try and make it linear, because then everything will be simple. Okay, and then obviously these are the two very big theorems which make our life very a lot more easy. Right? And they are based on linear systems. So for that, first we need to know what a linear system is. Okay, and this is very important, not just for this class. As I said, as engineers, you'll always be dealing with linear systems, so you should be clear. How many of you are taking signals and systems? How many of you have taken signals and systems? Awesome. Okay. So if you have taken signals and systems, I'm assuming you know what a linear system is. Okay. So let's say I have a system. So I have an input x of t and an output y of t. I'm saying this is a linear system. So how do you mathematically define that? What do you recall? What does it mean for a system to be linear?
No higher order power. Two.
No higher order what?
Like a variable power 2.
I see. So okay.
Squared.
The output is a scalar multiple of the input.
Okay. Let's see. All right. So let's say. Moshe. Okay. So output is a scalar multiple of input. Let's say I have my input is x of t, and my output is 5 times x of t. Okay. So this can happen with a linear system. Okay. Let me take another example. Let's say, for example, if this was sine omega t, and this was 5 times sine omega t, this is a linear system. Okay. So if my input is sine omega t, let's say if my output is 0.5 times sine omega t minus pi over 4, is that a linear system?
Yes.
So is the output a linear multiple of input? Is output a linear multiple of input? Obviously not, right? Because there's also a phase shift. So is this can this be with a does this can you conclude from this that this is not a linear system? So if you start, then that definition that the output should be a multiple of input is not complete, right? You can have a linear system where the output is not a linear multiple of your input. Right? If this is not a linear system, then all your RC circuits are not linear systems.
Right.
Right? But at least you were told they were linear. Right? So then what is the definition of a linear system? Can you remind me your name?
Noel.
Noel.
Yeah.
Okay, so Noel? Noel. Okay.
Yeah. Does the input and output have to be linear in order for the system?
So okay, what do you mean by input and output are linear? What do you mean by input is linear?
I guess I don't know, a signal.
Okay, so what is a linear signal? Okay. Okay. So it's so I'm not sure if I stressed this in my first class. I will do this often, and I'm not trying to say, hey, you don't know that or something like that. But I'm trying to actually point out where your the holes in your understanding, right? So that's what I'm trying to do. So don't take this in an adversarial way, But I'll do this a lot. So just so you know. Okay. So what else? Yeah. No.
I think the only thing I've ever heard about that is you can't have like two, I guess, if you're graphing on the XY plane, you can't have two X points.
Okay.
Give you a-
All right. So I think what you're thinking about is a linear function,
Okay.
right? A linear function is like y equal to 5 times x,
Yeah.
right? So if you have what you're thinking of is, if you have a plot, then this is a linear function, right? If something is like this, which is not passing through 0, we call that an affine function. But it's still somewhat linear, right? But when what you're saying is, if a function is like this, that's not a linear function,
I was saying like,
right? Maybe like this,
yeah.
right? That's not even a function, right? So yeah, that's about functions. linear functions, right? Now we're talking about linear systems, right? So functions are like signals, right? So this straight line is a linear signal, you know, but now we're talking about systems, like signals and systems. So now we're shifting to what does it mean for a system to be linear? That's the question. Moshe.
That's right. So the sum of inputs should be equal to the sum of the outputs.
Okay. So I think what you mean to say is a linear combination of inputs should produce a linear combination of outputs.
Okay, that's what I'm trying to get at.
Right?
Multiples.
Sum of inputs, obviously inputs are not equal to
Right.
outputs, right? So what you're trying to say is a linear sum combination of inputs should produce a linear combination of outputs, right? And this is called what principle? Superposition principle. You've heard about that, right? And that applies to linear systems. Okay, so let's do this. So there are two properties a linear system should have. One is, so let's say I apply a signal x of t, okay, and I observe y of t. Okay, x of t can be anything. I apply x of t and I see at the output y of t. Okay, then if I go and apply, let's say some constant a times x of t, okay, then my output should be a times y of t. That means if I magnify my input, my output should be magnified by the same amount. Okay, this is property 1. Okay, and this is called uniformity property. Okay, so in second property, then if I am applying x of t, I see y of t. Then I go and apply some other signal y of t, and this can be x. Let's say this is x1 of t, and this is y1 of t. Then if I apply x2 of t, I see y2 of t. Okay, so these are just I grabbed one signal at once. Could be sinusoid, cosine, triangular, whatever. Applied it, I saw an output. I took another signal, applied it, I saw another output. Okay, then in a third experiment, at the input, I apply the sum of the signals. Then at the output, if this is a linear system, I should see y1 of t plus y2 of t. Okay, and these x1 of t and x2 of t can be anything. Okay, if I take two signals and sum them up and apply that to the input, at the output I should see the sum of the outputs of those individual signals. Okay, and this is called superposition principle.
All three of them are considered superposition?
Just the second property. Okay, so uniformity property and the superposition property, both of them combined makes the definition of a linear system. Okay, so let's see. Now here's a very simple property for a linear system. Let's see. So just to get our hands a little bit dirty, let's say we will denote our linear systems with f. That means my output y of t is, so let's say some f of x of t. Okay, and then f is a linear system. Then what is f of 0? F of 0 means I'm applying 0 signal. 0 as function, let's say constant function 0. What would be the output for a linear system? It should be 0. Okay, y of 0? No, so output should be a function of time, right? So if you're saying, is that what you said? That's a number, right? I want a function of time. I want a signal as an output. So input is a signal, output is a signal. So that means it's like 0 as function of time, right, which is constantly 0. That's the input. Its input is the function itself, right, system. So, you know, if you have a system, you feed in a signal and you get a signal at the output, right? So I'm feeding it 0 signal. What should be the signal at the output, right? Again, take 2 minutes, work in groups, let me know. You should be able to use these properties and come up with the answer. Okay, let me simplify the task. The output will also be 0. So then the task for you guys is prove that. For a linear system, if I don't give any input, there should not be any output. Okay, and there's a small caveat there. I'll tell you what the caveat is later, but for now prove this using the properties which I just said. These are the two properties. Uniformity and superposition. Right, I want you to prove that if you prove that if you apply a 0 signal, you'll get 0 at the output. At 0 as a function of t, you get 0 as a function of t. I'll give you another hint. All you need to use is the uniformity property. Volunteers to prove it on the board? Jeremy, right? What? Jeremy, is that your name?
Yes.
Okay. Do you want to prove it on the board?
I believe in you.
Again, you have to convince them that your proof is correct.
Yeah.
Okay. So think of Jeremy as me trying to explain the proof. So you should ask him questions, and if he doesn't explain it to you.
So we know from the uniformity property that a scalar times x of t gives you the scalar times y of t. In this case, we have f of 0. So if a is 0, here, 0 times x of t is 0. And since we have to have the same scalar, it has to be 0 on this. Does that make sense? 0 times anything is 0.
Are you saying that f of 0 is alpha, not the x of t?
No, I'm
Which one is
saying-
0? Alpha or
Yeah, see, I see a t attached to it on the inside. F of 0 of t.
Right.
Zero function has a zero across.
Oh, I think you have it backwards. I don't think there's a scalar, but anything times 0 times a scalar is 0. If you said that 0 is a, I think x of t in this case is 0.
I mean, if x of
Y
t is 0,
No,
Right.
I
Okay.
think you had it switched.
Yeah.
Like you
But
said that
I think
the scalar
okay,
is 0.
both are correct. I think what Jeremy is saying is a can be 0,
Oh, okay.
right? And x of t in this case has to. So you both have, if you're correct. So maybe you'd have to come to a reconciliation between you both. So right, Jeremy has it's almost there, right? And what Noah is saying is an extra point you have to add into completely rigorous to complete the proof. Let's say no. Thank you, Jeremy. Right, you're almost there. It's the only reason I'm saying this that proof is not correct is because of a technical, right? And I will go through how to actually account for that technicality. Okay, here's the thing. This is how you actually prove it. Okay. So what I'm saying is, let's say if I apply a 0 function, and I don't know at this point what the output is. I'm trying to figure this out. So let's say the output was y of t, something. Okay. Then if I apply some a times 0 of t, then I should get a times y of t. Right? So what is a times 0 of t? This is equal to 0 of t. Right? So I have the same inputs. That means the output should be the same. Right? So it means y of t should be equal to a times y of t. What does that say about y of t? When is this possible? When y of t is 0. Right? Because I'm saying a can be anything. Right? So if a can be anything, the only way this is possible is if y of t is 0. Right? So it's simple then. So you take this to the left hand side, then you get 1 minus a times y of t is 0. And I'm saying a can be anything, right? So I can make a not equal to 1. Right? In that case, I'm saying then y of t has to be 0. That's how you prove that. Okay. So for a linear, so you see how when you're trying to prove mathematically, you have each step has to make this sort of sense. Right? Technically, it has to be correct too. Otherwise, you could go wrong. Right? That's the reason why you have to be very technical. Okay. So what's the bottom line? That for a linear system, you'd have no input, there should be no output. The caveat is we're only talking about stable conditions. Right? So there could be transient states, in which case the output will not be 0. But stable conditions, it has to be 0. Okay? Any questions here? Right, so today we saw the equivalence between Norton's and Thevenin's, and we saw what a definition of a linear system is, and Norton's and Thevenin's theorem apply only to linear systems. Okay, so next class we'll dig a little bit more into linear systems. We are supposed to wrap up circuits 1 and 2 this week, but it's going to go into another week. So I'll try to make, for other material, I'll try to make some videos.
I'll take that one. Yeah.